Now, none of these, by the way, are the fundamental theorem of line integral, because we won't get to that today. I don't think, at least. Let's see how many questions there are before it is. No, we won't get to that today. But anything that's called the fundamental theorem is probably a biggie. And what this does is that it found a nice, easy way to calculate line integrals. You know how we've got three methods from, the ugly square root one, turn all the dx's and dy's into x's and dt's, remember those kind of ones? And then the third one is doing the FDR one, right? And so each one of those is a little bit tricky, and can sometimes end up with really heavy duty integration, right? And what the fundamental theorem of line integrals was done, and I've got it at the tip of my tongue, I think it was Euler who figured it out, really clever mathematician, found out a way of doing that much easier. But we're not going to get to that today. But we need to know how to do these things, because these things are going to lead up to the fundamental theorem. So I mentioned it yesterday, and it kind of surprised me that the question had it. But remember that one where the integral was 0? And I said, oh, that's cool. It must have been a conservative field. I used that term. So let me explain what was going on here. We are looking at line integrals that essentially look like that format, right? F is a vector field, so we're talking only about 2D vector fields. So can you imagine we've got, God, it takes forever to draw these arrows. But can you imagine we've got maybe an explosive vector field, right? Where everything's shooting away from the origin, right? And then you're going to have a curve C passing through this vector field. And the line integral is essentially finding the work done as you travel through it. So that's the type of question that we're going to be using the fundamental theorem of line integrals to solve. So what is a conservative field? Right, you take your function f, and this thing here tended to look something like this, 2x plus y, y squared minus 3, that's the look to it. Call this guy P and call this guy Q, right? So whatever the x component of your vector field is going to be called P. Whatever the y component of your vector field is, we're going to call that Q. And if this is true, if the derivative of P with respect to y is the same as the partial derivative of Q with respect to x, you have a conservative field. And you can only do the fundamental theorem of line integrals when it's a conservative field. So kind of your first step is, can I actually use this trick that you don't know what it is yet, but can I use it? Oh, excuse me. My apologies, everyone. That was the project manager telling me I have to sell one of my kidneys to pay for the repair. Anyway, back to this guy. You are a conservative field if this is true. If this is not true, then you're not. I randomly made this one up, so I'm not sure if it's going to work or not. So let's find out. If you differentiate this guy with respect to y, you get 1. And if you differentiate this guy here with respect to x, you got 0. So this is not a conservative field. Agreed? So it's not a hard thing to check, right? You just take the derivative of this guy with respect to y, and you compare it to the derivative of this guy with respect to x. And if they're equal, conservative field. And if they are not, well, they're not conservative field. So an example would be, let's find one that works. Okay, this one works. So in question 2, it's my version 2, the vector field that we're going to be dealing with is y squared take away 2x. That guy is the other one. And so let's check our test. I've got the test here. So he's p, he's q. So the partial derivative of p with respect to y should be equal to that guy. Okay, if you do this guy with respect to y, you get 2y. And if you do this guy with respect to x, you get 2x. So this is a conservative field. Are you comfortable that it's a pretty straightforward test? Right? We're only doing it with 2-dimensional vector fields, but p and q, if this is true, and I did an oopsie. Now it's true, right? 2y is equal to 2y. Now, vector fields that are conservative are very interesting because if they are, this is the second bit we're going to talk about now, if they are a conservative field, then there is a normal function, right? This is just a normal, you know, x squared plus y squared minus 2xy, right? As a typical function that has this property, that the gradient of this function is the original vector function. So we are going to now figure out how to find this function f of xy, little f of xy. And this function, little f of xy, even has a name because it gets used so much. It's called a potential function. And evidently, engineers love conservative fields, and they love to find things called potential functions because evidently they're important for whatever reason. I don't care, right? But that's what they are. So since this guy is a conservative field, I know that there's some function that has the property that this thing is equal to f. Agreed? Now, the gradient is the partial derivative with respect to x and the partial derivative with respect to y, and it's going to equal this guy. So I just need to figure out what the function is whose partial derivative with respect to x gives you this, and the partial derivative of that same function with respect to y gives you that guy. So what we do now is we set up the two relationships. Here is the first relationship. So far, so good. Now, you might not need this line, but I'm hoping to put it in for emphasis. That's essentially what we're writing, isn't it? That the partial derivative of f with respect to x is that. We're saying the derivative is this. If you want to undo a derivative, then shouldn't you integrate? So I'm now going to integrate this expression with respect to x, right? So you got to remember, x is the only variable, everything else is 42. So if you integrate y squared with respect to x, you get xy squared. And if you integrate negative 2x with respect to x, you get negative x squared. So far, so good. Right, when you integrate something, integrate it. Now, shouldn't you have a plus c, right? Arbitrary constant. Well, in this world, the plus c is a unknown function of y. Now you may think, well, why can't I just say plus c? Why do I call this g of y? If this was y cubed plus 2y, when you differentiated it with respect to x, wouldn't it disappear? And so we don't know what the arbitrary constant is, but it could have y's in it, couldn't it? And so that's what that's for. So that is my first version of what f could be. Now I'll go to the second half, and we have f of y, and f of y is equal to 2xy. And we're going to integrate it with respect to y. And if you integrate this guy with respect to y, don't you get x y squared? Would you agree? Add 1 to the power, divide by the new power. And a plus c. Well, when you integrate with respect to y, you have an unknown function. I'll call it h of x. Now I'm going to put the two guys one underneath the other. So far, so good. This is what we know about the function. This is what we also know about the function. What we now do is we merge these together. And the answer is that. If you've both got them, it's in the answer. If one of them has it and the other doesn't, it's still in the answer. But you might say, well, how come that doesn't have a minus x squared? Isn't h of x the placeholder for where minus x squared would live? Now, this one doesn't have it, but can you pretend this one had plus 2y in it, just for argument's sake, right? Wouldn't there be a plus 2y in the answer? And why is plus 2y okay? Because this guy over here allows you to have it, right? So everything, the two pieces, when you put them together, kind of get melded. So if one of them has it, the answer has it, right? If both of them have it, the answer has it. And this is our potential function, our little f of xy. And right now, I'm not telling you why you want to know that, but trust me, you will want to know that because it's going to make line integrals very easy to calculate. So once you know this guy, line integrals become really, really easy to do. Let's try another one. This is a version of question 3. I have y squared e to the xy. I have a 1 plus xy e to the xy. And we are being asked to determine, first, is it a conservative field? And then if it is, we have to find the potential function. I'm going to call this guy P. I'm going to call this guy Q. I'm going to find the derivative of P with respect to Y first. All right, if you differentiate this guy with respect to Y, you're going to have to do a product rule. So it's going to be f dash j plus f of j dashed. And if you differentiate this guy, you get 2y. And leave that guy alone, you're going to get that. And leave the first one alone, you're going to get y squared. And if you differentiate e to the xy, you get e to the xy times what? I'm differentiating e to the power of xy with respect to y. You get e to the xy times something.
Times x.
Right. Are we comfortable about that one? That's what it's equal to. Okay, let's see what the other one looks like. Let's do this one with respect to x. So I guess I should put q up here. Nah, I can use it. Call this f, call this g. So you differentiate with respect to x and you get just a y. And you leave the other guy alone. Plus, you leave this guy alone. And you differentiate this guy with respect to x. And you will get e to the xy times a y. So I have this guy, I have this guy, and I have this guy. And these two are the same, so we can combine them. And as unlikely as it seems, aren't they equal? Xy squared. Oops, I forgot my square. Xy squared. Right, they're equal. Conservative field. Any questions before we move on to finding the potential function little f? Okay. Now we are trying to find a function, little f, that has the property that its gradient is equal to this guy. So the partial derivative with respect to x and with respect to y is going to be that guy. And that guy. Right, I'll match up those two. The partial derivative of f with respect to x is that. So if I integrate with respect to x, that guy's just a number, so is that guy just a number. Now, if you integrate this guy, you will get y squared e to the xy. But won't you also get, a, you know, if it was e to the 2x, wouldn't I get times a half, right? If it was e to the 10x, wouldn't I get times 1/10? In this case, wouldn't you get times 1 over y? Are you comfortable about the xy bit generating that 1 over y bit, right? If you integrate e to the 5x, you get e to the 5x times a fifth. That y is like 5. Now that tidies up a little bit, and you get y e to the xy plus some unknown constant. Well, since you're integrating with respect to x, the missing thing, I'm going to call it g of y. Match up the second one. And I'm going to rewrite this guy as e to the xy plus xy e to the xy. And now I'm going to try and integrate it. Okay, you want to integrate this guy with respect to y, you get e to the xy times 1 over x. And if you want to integrate this guy with respect to y, won't we have to do, would you believe it, not where I expected to find one, isn't this going to be an integration by parts? So it's going to be f dashed capital G, take away the integral of f dashed capital G, in this case, dy. Right, if you differentiate this guy with respect to y, you will get x. And if you leave this guy alone, you will get, you integrate this guy, you'll get e to the xy with respect to y with a 1 over x. Takeaway, if you differentiate this guy, you get, with respect to y, you get x. And if you integrate this guy, you get e to the xy times a 1 over x dy. Not sure about what's going on here, but I'll trust the math, see what happens. They cancel out, and so I'm going to get that.
Mr. Roberts,
Yes.
couldn't that also theoretically be done with a U sub?
Well, this one here?
Or the
here?
one below that? Yeah. Like the U sub is x, y, and then you integrate, or not integrate, you take the derivative in terms of y, and then you just get 1 over x times e to the u. Du.
Wouldn't the xy get you a u?
Yeah. Or, oh yeah, and then you'd still have a u.
And then you still have to do it. Yeah.
Okay.
It's worth a try.
Okay. Thank you. Sorry.
No, I'm not quite happy with this. I'm still trusting the math that it's going to come out good. I just don't feel good that it's going to come out good yet. But I'll keep going. If you integrate this guy, you get e to the xy times a 1 over x. Oh, gone and gone. E to the xy. Now, if that first one, where's the first one? Hiding. I don't want that y. Darn it. If that was missing, it'd be a perfect fit. So am I missing a y? Maybe that's what I'm missing. I'm missing a y.
Is it when you were doing the integration by parts, is it just fg instead of f dash g for the beginning?
There it is. Yeah, there's the y.
Or no, on the other side.
Oh, where?
Isn't isn't there not supposed to be a dash there? And then
It is. That is it, and that is it. So that's good, which kills it. And what do you get when you do that then? You're going to get, oh, I've made a mess too early. So we're starting again. If you replace the formula with that version, which I should have done this first time, can you trust me that you eventually get y e to the xy? Plus some guy that's an arbitrary constant. And that means that if we write the two pieces down, the one that I did the first time came out perfectly fine. The second one, if I did it correctly, would have came out looking like this. And when you merge them, you get that. Let's check it. Yeah, that's what the answer is. You're looking puzzled, Christian. What's going on here? Just a lot of steps?
Yeah, I'm just trying to pay attention.
Okay, nothing wrong with that. Paying attention's good. So I'm going to try and pay attention with the next one. After me mumping on about not having an integration by parts, they finally gave me one and I managed to screw it up. Go figure. So, yeah. This vector field is y e to the x plus a sine of y, and then it's an e to the x plus an x cosine of y. And this is the p, and this is the q. And just to save time, can I tell you it is a conservative field, right? Just trust me, it works. So let's just move into phase 2 and get more practice at finding the potential function. So the partial derivative of this guy with respect to x and y is the same thing as this guy here. So match 1 with 1. So the partial derivative with respect to x is that guy. So when you integrate it, if you integrate y(e) to the x with respect to x, you just get y(e) to the x. And what do you get if you integrate sine y with respect to x? What do you get if you integrate sine y with respect to x?
X sine y.
Yeah, just like 5 gets you 5x. And since I'm doing it with x, there's some arbitrary constant called h of y. That's just a placeholder in case there's some bits left over that we can't match. Put a big circle around it so it's easy to find. Then I'll move on to the second one, which is that guy. And if I integrate with respect to y, what does e to the x get you when you integrate with respect to y? Any takers? What does e to the x get you when you integrate it with respect to y?
y(e) to the x.
Yeah. Isn't it just like 42? It's just a number, so tag a y on it. Now, if you integrate a cosine, an x cosine, won't you get an x sine of y? And the arbitrary constant, since we're looking at y's here, will be some function in terms of x. Now, when you merge these two guys together, would you agree it's a really nice fit, isn't it? Share, share. So the potential function is y(e) to the x plus x sine y. I hope the more we do, the more comfortable you are with this process, right? Let's move on to one last one of this type. And then I think I might just tell you what the fundamental theorem of line integrals is, which is why am I doing all this? So for the last one, let's do question 5, or a version of it. We have 3x squared y plus y to the negative 8. And we have x cubed take away 8xy to the negative 9, just that guy. And we'll assume that it's conservative because it is. And we'll jump into the second part of the process then, finding the potential function. Once you've done enough of them, I hope it becomes like just a process, almost mechanical. Right, if you match the first one up, that's this guy with this one, you get that. And if you integrate with respect to x, you add 1 to the power of x and divide by the new power, and you get that. And this ugly thing is just treated like a number, so when you integrate it, you get an x. So that's my first version. When we match the second, we get Oh, I forgot. Since this is x, it's going to be some arbitrary function of y, call it that. So here is second matchup. Integrate with respect to y. Well, x cubed just gets you x cubed y. Add 1 to the power and divide by the new power. And you get that, plus some arbitrary function of x. And that's my second answer. And oh, we got a perfect match here. There wasn't even a little bit that one had and the other didn't. So we have our potential function. It's that guy. Are we good with this, or do you want to see one more? Or do you want to move on to tell you what this thing called the fundamental theorem of line integrals is? You feel you've seen enough of these to see it's a process, right? Okay, good. Well, I want you to imagine that we have a conservative vector field, right? I want to find the line integral from some curve C. So we're going to start here. And this guy here is going to be, I don't know, the point, I'll call him x1, y1. And it curves all the way up to here. And that's going to be x2, y2. So my curve C is this red curve from x1, y1, right, to the point x2, y2. And I want to find that line integral, right? Probably because I want to know how much work is done in this little aircraft flying through this storm, right? From here to here. Right? Now, if this is a conservative field, the answer to the line integral is that it's the value of the potential function, right? You know those little f's that we've been finding? The value of this potential function at the destination point, take away the value of the potential function at the start. And you might say, well, but that curve could be lots of different curves. It could be a curve that went this road. And it could be, I'm going to show the colors here. It could have been a curve that did all sorts of weird stuff. The fundamental theorem of line integral says it doesn't matter what path you take to get from here to here, right? Doesn't matter actually what curve you take. All that matters is where you started and where you finished. So the difference in the potentials is the answer. Kind of cool. So when we find these potential functions, right? In fact, let me use this one as an example. Suppose I had this function and I told you that C was, I don't know, x equals t squared plus e to the t, and that y was t cubed plus 1 over 2t, right? And I told you it started at t equals 0 and it finished at t equals 1, right? So imagine we had that guy. Now, when you look at how ugly that function is, can you imagine how much trouble we would have converting everybody into t's and doing all this r dots and r dashes and Oh God, can you imagine how horrible that integral would look? Now, we already have solved the major part of the problem. We found out it was a conservative field, and this is our potential function. So if someone went and said to you, what is the integral, right? What's the line integral for this curve on that guy? We would be saying, all I need to know is where do you start and where do you finish? So let's find out who they are. I'll call them P and Q. P is when t is 0. So that'd be 0 squared plus e to the 0, which is, I'm going to have to change this guy, put a 1 there, is 1. And the y coordinate is 1 over 1 is 1. Okay. And the q is what happens when it's 1. So what do you get? You get 1 plus e, and you get 2 plus 3. There. So you started at the point 1, 1, and you finished at this point. I know the potential function. It's y e to the x plus x sine y. So this line integral is just going to be the value of the potential function at 1 plus e 2/3. Take away the value of the potential function at 1, 1, right? That's all you need to evaluate. So I will take this expression and evaluate it at these points, and this expression and evaluate it in that one. And God, it's going to be ugly, but never mind, at least we can get the answer. Right, it's going to be 2/3 e to the power of e plus 1 plus 1 plus e, the sine of 2/3. That's the first bit. Take away what you get when you plug in 1, 1. When you plug in 1, 1, you get e plus the sine of 1. And that's it. I mean, I guess I could write it down. But 2/3 e to the e plus 1 plus 1 plus e, the sine of 2/3. Take away an e, take away a sine of 1. Now, if you try to do this guy using that horrible curve and you set up the integral, I would say without fear of being wrong that you wouldn't be able to do it. I think the integration would be so horrendously ugly that it wouldn't be feasible. So the fundamental theorem essentially says, if you have a conservative field and you're doing a curve, just find out where the curve starts, find out the coordinates of where it finishes, and plug it into here, the potential function, right? The value where it finishes, take away the value where it ends. Can we pretend that that is a conservative field, just for argument's sake, right? And the curve C is actually x squared plus y squared equals 1. In other words, you go round an entire circle. I don't need to do any calculations. I do not even need to find the potential function. If you are a conservative field and your curve C is a loop, a circle, an ellipse, what's the answer going to be every single time?
Zero.
Yeah. Because in a loop, don't you start and finish at the same point? You can even pick which point you want to start and finish, right? And if you start and finish at the same point, won't the potential function be equal? right? Because you start at 0, 2 and you finish at 0, 2. Right? So if someone gave me a conservative field and they drew a loop and they said, that's my curve C, I could spend 20 minutes finding the potential function, but I wouldn't bother when I just say the answer is going to be 0. So if it's a closed loop, in other words, you start and you finish at the place at the end, you're always going to get 0 in a conservative field. Can you remember the one that I was kind of happy or interested in when I saw it? Had a circle inside one. Remember that one? Yesterday? Can you see now why the answer was bound to be 0? Because the curve C was a circle. And the vector field happened to be conservative. And I kind of knew it would have to be. Any questions? We learned some cool stuff today, didn't we? We learned some integration that you might not be expecting. And we found out what a conservative field was and what a potential function was. And lastly, how that allows us to find line integrals very easily, compared to what it would be if you did it other ways. Right, last name, bye-bye. I'll hang about. Remember what I said about there'll be a new Zoom link starting, I hope I said that anyway. There's going to be a new Zoom link starting on Monday, so keep your eye open for it in Canvas. Right, I'll wait for any questions, otherwise we're out of here. Okay, who's first? Christian, what's your question?
Oh no, I just figured it out. I just got it.
Oh.
Thank you.
Okay, that was good. I'm using telepathy now to help students, Mia. Is that not impressive?
It's crazy impressive.
Thank you. Right, anyway, you got a question?
Yes, I don't know if I'm just having a brain fart or what, but I can't seem to solve number 10 on the 15.9 homework.
All right, let me go back to that one and see what number 10 is. 15.9. Are we talking 16.2? Is it line integrals 16.2?
The change in variable.
Oh, it's an earlier question. Okay, I'm in the wrong section.
Yeah.
Give me a minute to find it. So was that the last one, or down close to the last one?
It's number 10, so it's like
Okay,
almost
let's
like
find it on triple integrals. Change of variable. Finally found it. Okay, looks like you were good up until that point. So this one's second last one. No, it's not. God, there's a lot more than I thought. Question 10.
Yes.
Okay, so your answer is half the size. So,
Oh.
okay. So it might be just a simple arithmetic mistake where you lost a 2 somewhere.
Yeah.
But let's go through it in case it's more serious than that. So
Okay.
you've got a double integral of r, and the function is 2y squared. You've got a dA, and your substitutions are going to be, oops, u equals xy, and the other one is v equals x y squared. Yeah, is that the guys you've got to work with?
Yes.
Okay, so we really need to rearrange these guys, because what we want is x in terms of, or y in terms of, right? So we can do the Jacobian, but there is a way around that. The shortcut, and I'll do it over here, is that you can actually find this Jacobian
Mm-hmm.
and then just turn it upside down. Okay. Although you may have to do some substitution, because when you're finished, whatever method you do it, don't you want the answer only have u's and v's in it, right?
Yes.
So we're going to do with respect to x, with respect to y, then v with respect to x, and then v. with respect to y. And let's see what we get. If you differentiate this with respect to x, you get y. And if you do it with y, you get x. If you do this one with x, you get y squared. And if you do this one with y, you get 2xy. And major diagonal is 2xy squared. And minor diagonal is xy squared. So what you end up with is an xy squared, which luckily enough happens to be v.
Got it.
We could do it, right?
Yeah.
And so the Jacobian that we want is just the reciprocal of that. So that actually came out quite good.
Mhm.
Now, if we look at, back to this question again, if we then look at the next piece, which is all the limits, you know, we have an xy6 and an xy8. Well, that simply is u. So u goes from 6 to u goes to 8. So there's the limit integration for the u variable. And then the other one was xy squared was 6 and xy squared was 8. And that gave me v equals 6 to v equals 8. So that's good, right?
Yeah.
That was pretty easy transfer. I should do the 2y squareds. I'll do them kind of as we're going through it. So u is going 6 to 8. V is going to go from 6 to 8. 2y squared is a pain in the posterior because I need to turn that guy into u's and v's. Right, so if I go to the side again and see what we have to work with here, I have this guy, I have this guy, and somehow I'm going to try and figure out a way of figuring out what 2y squared is. And an obvious come into my mind. If I divide them, okay, that'll work. Can I switch these round? There. If I divide them, v over u equals y.
Got it.
So
Yeah.
v squared over u squared gets me y squared. So 2y squared gets me 2 of them.
Okay.
So I have 2v squared over u squared. I have a Jacobian, which is 1 over v, and I'm going to do a dv and a du. How does that look compared to what you were doing? Does it look familiar or not?
Yes, that's what I had.
Okay, so we are. Did you do it the same way I did it, or did you figure another way of doing it?
I did it the same way you did it.
Okay. So essentially looking at this guy.
Yes.
Okay, so might as well separate them then. 6 to 8 gets me a 1 over u squared. And then a 6 to 8 gets me a 2v. That guy is v squared from 6 to 8. That guy's negative 1 over u from 6 to 8. And what am I going to get? I'm going to get 64 take away 36. I'm going to get negative an 8th add a 6th. Just let a calculator figure it out. Negative 1/8 add 1/6 multiplied by 64 take away 36. Make that guy a fraction, and I get 7/6. And the right answer was 7/6.